Imagine an element so fierce that it can make water burst into flames and glass dissolve into liquid. Sounds like science fiction? Meet fluorine, a pale yellow gas that holds the title of the most reactive element on the periodic table. Fluorine is infamous for creating some of the most destructive acids known to chemistry, the kind that can eat through almost anything. Yet despite its wild behavior, fluorine is also a secret ingredient in everyday life, from the fluoride in your toothpaste to the non-stick coating on your frying pan. How can one element be responsible for both horrific acids and helpful products we use daily? Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, hype, subscribe and hit the notification bell so you will never have to miss another episode. Also, make sure to fill in the poll in the post section of the channel for next week, as we will be discussing another element again. Now here we got another cube again, where there seems to be nothing in it. We have seen this before in the case of hydrogen, neon and xenon, for instance. So the question is, can we, like with these previous ones, prove that there is actually something in the cube? Well, in this case, the answer is disappointing. For fluorine as well as for chlorine, we cannot use the good old Tesla coil to show these gases. In this case, we just have to trust engineered labs that there is fluorine in this cube. And that, of course, brings us to the question which everyone always wants answered: can you lick it? Well, if you somehow exposed your tongue to elemental fluorine gas, the reaction would be immediate and severe. Since your mouth is full of moisture and fluorine reacts violently with water to form hydrofluoric acid and reactive oxygen species, you would be immediately in trouble. This means that the instant fluorine touches your saliva, it would begin chemically burning tissue. Fluorine is an extremely powerful oxidizer, so it would attack the organic molecules in your cells, damaging lips, tongue, and your throat within seconds. And you thought rubidium was bad. Well, the reaction also releases heat, which adds to the injury. Even brief exposure to concentrated fluorine gas can cause serious respiration damage, if inhaled, including chemical burns in the lungs. Now, the hydrofluoric acid formed during the reaction makes things even more dangerous. Unlike many acids that mostly damage surface tissue, hydrofluoric acid can penetrate deeply into the flesh and bind to calcium and magnesium in the body. This can disrupt nerves, damage bones, and in severe cases interfere with heart function. Now, what makes hydrofluoric acid particularly hazardous is that the full extent of the injury may not be immediately obvious at first. In short, contact with intermittent fluorine would result in rapid chemical burns and potentially life-threatening systematic toxicity. It is one of the most dangerous substances to expose to living tissue. So can you lick it? Listen to the periodic licking table. Don't. And can you snort it? Take a wild guess. The story of fluorine's discovery begins with a mineral called fluoride, also known as fluorspar. Long before fluorine was recognized as an element, in 1529, a German scientist named Georgius Agricola noted that adding fluoride to certain ores helped them melt ore easily during the metal smelting. In Latin, Agricola described these fluxing minerals with the word fluor, meaning to flow, because they made molten metal flow better. This is the root of the name fluorine. The mineral fluoride got its name from this property. It was originally fluores or fluorspar, and later the element isolated from it inherited the name fluorine. In a sense, fluorine's name literally means flowing, hinting at its early use in helping things melt or flow. Little did those early metallurgists know the harmless-looking fluorspar held one of the most reactive elements trapped inside. Fast forward to the 1700s, chemists began to investigate the strange properties of fluoride. In 1764, Andreas Marggraf in Berlin heated fluoride with acid and produced an acrid solution that could etch glass. This was hydrofluoric acid, HF. Although at the time they called it fluoric acid, Swedish chemist Carl Wilhelm Scheele repeated the experiment in 1771 and confirmed that this acid was unlike any others. Now, it was incredibly corrosive, eating away glass containers themselves. These early chemists realized that the acid contained a new substance, but they couldn't isolate it. They suspected that inside fluoric acid was a new element, analogous to chlorine in hydrochloric acid. However, every attempt to separate this mysterious element ended up in failure or injury. By the early 19th century, the idea of a new element in fluorspar acid was solidifying. French physicist André-Marie Ampère corresponded with English chemist Humphrey Davy about this curious acid. In 1810, Ampère suggested that fluoric acid was a compound of hydrogen with an unknown element similar to chlorine. Ampère even proposed a name, fluorine, derived from the mineral fluoride, plus the "in" suffix used for elements like chlorine. In 1813, Humphrey Davy announced the potential discovery of this new element and adopted the name fluorine. The stage was set. Now someone had to actually isolate the pure element fluorine and prove it existed. Isolating fluorine, however, turned out to be a chemist's nightmare. Fluorine was trapped into compounds like calcium fluoride or hydrofluoric acid, and any attempt to free it resulted in disaster. The element reactivity was so extreme that as soon as it was liberated, it would attack whatever was nearby: the container, the equipment, or the chemist. Throughout the 1800s, a series of brave or perhaps crazy scientists tried to isolate fluorine, and many paid a terrible price. Now, they became known as the fluorine martyrs. Humphrey Davy himself suffered painful injuries when experimenting with hydrofluoric acid. He inhaled fumes that damaged his eyes and lungs. French chemists Joseph Gay-Lussac and Louis Thénard were poisoned by the vapors of their attempts. Thomas and George Knox, Irish chemists, built special apparatus from fluoride mineral to contain the acid. Even so, both were severely poisoned. One nearly died, and the other was bedridden for years. Several other researchers, including Pauline Loyet, Jérôme Nichols, and George Gore, were severely injured or killed while trying different methods to isolate this elusive element. Each time fluorine's incredible aggressive nature thwarted their efforts, it seemed impossible to contain. Now, the problem was that hydrofluoric acid and fluorine compounds would attack all the materials the chemists tried to use. Glass, ceramics, metal, nothing could withstand fluorine. Additionally, hydrofluoric acid itself is not an easy substance to work with. It's extremely corrosive and also not a good electrical conductor, which made early electrolysis experiments fail. Finally, the breakthrough came from the French chemist named Henri Moissan. After many years of fluorine-defeating chemists, Moissan, who had studied under another fluorine researcher, Edmond Fremy, devised a clever approach. In 1886, Moissan prepared a mixture of potassium bifluoride and dry hydrofluoric acid and cooled it, making a solution that could conduct electricity. He built a special U-shaped apparatus made of platinum-iridium alloy, a material resistant to fluorine's attack, and with carbon electrodes, and kept everything cold and free of moisture. Then he ran an electric current through the cell. This setup succeeded where all the others have failed. Moissan saw bubbles of gas forming at the anode, which, to his excitement, were fluorine gas. On June 26, 1886, after 74 years of collective efforts and many injuries, elemental fluorine had finally been isolated. Moissan's triumph was recognized, and in 1906, Henri Moissan received the Nobel Prize in Chemistry for this achievement. The Nobel Committee applauded the great experimental skill with which he has studied that savage beast among the elements. Now, this wording was no exaggeration. Even Moissan himself suffered poisoning several times in the process, and in fact, tragically, he died in 1907, not long after receiving the prize, possibly weakened by years of toxic exposure. In its elemental form, fluorine, F2, is a gas at room temperature and pressure. It has a distinctive pale color, though in a thin container it might look almost clear, as we can see in this cube. Now, if you could safely take a sniff, not recommended, you would find it has a sharp pungent odor reminiscent of chlorine, a choking bleach-like smell that warns you immediately of its toxicity. Now, fluorine gas is relatively light. Each molecule is 2 fluorine atoms, making it weigh about 38 atomic mass units. Its density is about 1.3 times the mass of air, so it can linger low to the ground. Under cold conditions, fluorine gas will condense. It turns into a bright yellow liquid at around minus 188 degrees Celsius or minus 360 degrees Fahrenheit. Cool it further and it freezes into a solid at about minus 219 degrees Celsius or minus 300 63 degrees Fahrenheit. Now, interestingly, solid fluorine comes in two forms: a soft, transparent form when just frozen, called beta fluorine, and an opaque, harder form called alpha fluorine when cooled a bit more. In fact, the phase transition between those solid forms is so energetic that it can become explosive. Even freezing fluorine can be a violent event. This gives you a hint of just how energetic this element is. On the atomic scale, fluorine is atomic number 9 on the periodic table, belonging to the halogen family, group 17, and this is the lightest halogen, and it has 9 protons in the nucleus with 9 electrons buzzing around. One interesting thing, all natural fluorine atoms are the same. There's only one stable isotope, fluorine 19. Every atom of fluorine in your body or anywhere on Earth has 10 neutrons and 9 protons. This uniqueness has a side benefit in nuclear technology, as we will discuss later. Now, fluorine's most outstanding atomic property is its electronegativity, a measure of how strongly an atom pulls on electrons. Fluorine is the most electronegative element of all. It has an almost insatiable appetite for electrons, which largely explains its aggressive behavior in reactions. It also has a very high first ionization energy. Now, what does that mean? It doesn't give up its own electrons easily. And a high electron affinity, it eagerly grabs other electrons to fill its outer shell. In simpler terms, a fluorine atom is just one electron shy of a full outer shell, and it will stop at nothing to get that electron, because every element basically wants to be a noble gas. Now, this makes fluorine atoms extremely reactive, as they seek to bond with nearly any other elements available. Now, if you think of fluorine as a chemically cranky little atom on a mission to complete its electron collection, you won't be far off. Fluorine gas is notoriously the most reactive substance in the periodic table. It will react with almost anything. In fact, chemists joke that fluorine will even make some otherwise inert things burst into flames. Now, this is not just a joke, it's been observed. For example, if you direct a jet of fluorine gas at a pile of sand or glass, which are normally thought of as non-flammable, the silicon in those materials will start burning as it forms silicon fluoride. Water, which we usually use to extinguish fires, will start burning in fluorine. Fluorine rips apart the water molecules to form oxygen and hydrogen fluoride, releasing heat and often causing a flame. Even substances like powdered steel, charcoal, or asbestos, a fire-resistant material, will spontaneously ignite when exposed to fluorine. This element is essentially a stronger oxidizer than oxygen itself. It forces materials to give up electrons, and often that process releases a lot of energy, flames, explosions, you name it. Chemists handling fluorine have to basically assume that anything that can possibly react with it will. Now, all the above probably makes you wonder, why is fluorine gas so reactive? Well, part of the reason is that the bond holding the two fluorine atoms together in the fluorine 2 molecule is relatively weak. Now, this may be surprising, but the two fluorine atoms, each fiercely negative, don't bond very comfortably. They repel each other's electron clouds. So the FF bond is easily broken, and when it breaks, each freed fluorine atom is a highly aggressive free radical that will latch on the nearest available other atom. Now contrast this with chlorine, Cl2, bromine, Br2, other halogens. Their atoms are larger and their bond isn't as strained, so they're not quite as eager to break apart. Fluorine, once broken in atoms, forms extremely strong bonds with other elements. It's like a relationship where fluorine says, I don't get along with my twin fluorine atom, but I'll form an inseparable bond with you instead. For instance, the bond in hydrogen fluoride or carbon fluoride bonds in teflon are among the strongest single bonds in chemistry. So fluorine's reactions tend to be vigorous. It breaks apart, then releases a ton of energy by forming new bonds. Fluorine reacts directly with nearly every other element on the periodic table, except for a few noble gases at normal conditions. It will attack metals, nonmetals, compounds, you name it. Only helium, neon, and argon are elements that essentially don't form stable compounds with fluorine under standard conditions. And even argon has a reactive species known under extreme conditions. Now, heavier noble gases like krypton and xenon do form compounds with fluorine, and when combined, for example, xenon hexafluoride exists, a discovery that surprised chemists in the 1960s, showing even the inert gases can succumb to fluorine's demand for electrons. Given this ferocity, elemental fluorine has to be handled in special ways. It can't be stored in ordinary glass bottles like chlorine gas can, because fluoride would etch or burst the glass. Instead, fluorine gas is often kept in steel cylinders that develop a protective fluoride layer inside. This layer passivates the metal, meaning it's a thin coat of fluoride that stops further reaction. One of the rare instances where fluorine decides to stay put. Any grease, organic matter, or moisture in a fluorine system is a huge hazard because fluorine will react explosively with those. Fluorine handles basically use metals like nickel and steel with clean polished surfaces, or sometimes containers made of teflon, a fluorine-containing plastic that amazingly resists attack by fluorine, and we'll explain that irony shortly. Let's talk about the acids of fluorine. The most well-known fluorine-containing acid is hydrofluoric acid, which is just hydrogen fluoride gas dissolved in water, or even the pure anhydrous hydrofluoric liquid. Now here's the twist. In water, hydrofluoric acid is a weak acid, unlike his cousins hydrochloric acid and hydrogen bromide, which dissociate completely into ions. That means hydrofluoric acid doesn't fully break apart into hydrogen plus ions and fluorine minus in water. It holds on to its hydrogen somewhat. You'd think that makes it tame, right? Well, you're wrong. Hydrofluoric acid is immensely dangerous and destructive, arguably more so than many strong acids. Why? Because hydrofluoric's toxicity and reactivity are off the charts. It can attack materials that other acids cannot, notably glass and ceramics. When hydrofluoric acid comes into contact with glass, silicon dioxide, it reacts to form silicon tetrafluoride gas and water, effectively dissolving the glass itself. Now, this is why you will never see hydrofluoric acid stored in a glass bottle. Plastic containers are used instead. Now, for living tissue, hydrofluoric acid is horrifying. It doesn't cause an immediate burning sensation on the skin, like, say, sulfuric acid might. Instead, hydrofluoric acid penetrates deep into the tissue while appearing deceptively mild on the surface. Once inside, it reacts with calcium in your bones and nerves, wreaking havoc. Even a relatively small splash of concentrated hydrofluoric acid on the skin can be fatal if not treated quickly, because fluoride ions can destroy calcium in the body and cause organ failure. There are unfortunate cases of people who accidentally got hydrofluoric acid on their skin, didn't realize the severity until hours later, resulting into severe tissue damage, bone loss, or death. Now, one gruesome story, often told in chemistry labs, of a scientist who spilled a bit of hydrofluoric acid on his leg. Initially, he felt only slight irritation, but days later, despite medical treatment, damage was so deep that he lost his limb and eventually his life. In short, hydrofluoric acid is not just an acid, it's a poison that penetrates and destroys from within. This is one reason why we call fluorine's acid destructive. But hydrofluoric acid isn't the whole story. Fluorine helps create superacids, acids far stronger than anything you will encounter in normal chemistry. For example, take fluoroantimonic acid. Now, this terrifying substance is made of mixing hydrogen fluoride with antimony pentafluoride. Now, the result is an acid that is 10 quadrillion times stronger than sulfuric acid. In technical terms, it has a Hammett acidity function value so low that it can protonate almost anything, even hydrocarbons that normally don't react with acids. Fluoroantimonic acid will instantly char paper, melt through glass and flesh, and release toxic vapors. It has to be stored in containers made of teflon, a fluorocarbon polymer, because even metal or glass containers would be destroyed by its fumes. So why is this acid so powerful? Well, fluorine's role is key. The anion, SbF- and F- combinations, are extremely stable and non-coordinating. Fluorine's high electronegativity means that once a proton, H+, leaves hydrofluoric acid and attaches to Antimony pentafluoride, the resulting complex ion doesn't want that proton back. Now, in other words, the proton is effectively free to damage, making the acid super strong. In simpler terms, fluorine makes weakly bond, highly stable negative ions that let the positive hydrogen ion rampage freely, hence an incredibly strong acid. This is why fluorine is behind the strongest acids we know. It forms the most stable conjugate bases like fluoride or hexafluoroantimonate, which means that the acids, hydrofluoric acid, etc., are eager to donate protons. So why does fluorine make the most destructive acids? Well, because fluorine, being so electronegative and reactive, forms compounds where the acidic proton is barely held on. Fluorine's presence stabilizes the negative part of the acid so well that the hydrogen can ionize completely, seeking something to attack. The result, acids that can dissolve glass, metals, and organics with equal ease. They are destructive in both chemical power and, in cases like hydrofluoric acid, in physiological effect. Interestingly, while fluorine in these contexts is terrifying, once fluorine is bonded in a stable compound, where it has its conveted electron, it can actually render substances very inert. A great irony of fluorine chemistry is that some of the most stable non-reactive metals are fluorine-containing compounds. Now, for instance, teflon, polytetrafluoroethylene, PTFE, is a plastic where carbon is completely bonded to fluorine. Because the carbon-fluorine bonds are so strong and the fluorine atoms shield the carbon chain, teflon doesn't react with much. That's why it makes such a great non-stick, chemically resistant coating. Now, sulfur hexafluoride is a gas where sulfur is surrounded by 6 fluorine atoms. It is incredibly inert and it is used as an insulating gas because it won't react or ignite. Now, given fluorine's nature, you might guess that you won't find jars of fluorine gas just hanging around in nature, and you'd be absolutely right. Elemental fluorine is so reactive that it doesn't persist in free state in the Earth's crust or atmosphere. Instead, fluorine is always tied up in compounds, primarily as the fluoride ion, combined with various metals. Now, despite being elusive as a gas, fluorine is not particularly rare in the Earth itself. In fact, it's the 13th most abundant element in the Earth's crust. There's more fluorine in the crust than there is carbon. It makes up around 600 to 700 parts per million of the crust by weight. Over geological time, fluorine has found its way into a variety of minerals. Now, the most important fluorine mineral is fluoride, or calcium fluoride, and we got it here. We met fluoride earlier as fluorspar, the melting flux. It typically forms a beautiful cubic crystal that can be purple, green, yellow, or clear. A large deposit of fluoride are found all over the world. Major producers today include countries like China, Mexico, and South America, among others. Now, the cool thing about fluoride is that when you shine a UV light on it, it will turn this beautiful color of blue, almost purple. Fluoride is the primary source for most fluorine production. The mining of fluoride and its purification is where fluorine's journey usually starts. Another key source is fluorapatite, a fluoride-containing phosphate mineral with this formula. Fluorapatite is a major constituent of phosphate rock used to make fertilizers. While we mine phosphate rock mainly for phosphorus, the fluorine in it doesn't go to waste. When phosphate is processed into fertilizer, fluoride byproducts like sodium fluoride or hexafluorosilicic acid are often recovered and used for other purposes. For example, water fluoridation or as feedstock for certain fluorine chemicals. A historically famous fluorine mineral is cryolite, sodium aluminum hexafluoride. Cryolite was critical in the aluminum industry. It was used as a molten solvent for alumina in the Hall-Héroult process of aluminum extraction. At one point, cryolite was mined from a massive deposit in Greenland and was one of the only sources of that mineral. However, natural cryolite sources have been exhausted, and nowadays we manufacture cryolite artificially for industrial use. Still, cryolite's existence shows how fluorine can form complex minerals. Other minerals like topaz, a gemstone, contain fluorine in their crystal structure too. Topaz is an aluminum fluorosilicate. Now, in nature, you will find fluorine in trace amount in soil, rocks, and water in the form of fluoride. Groundwater sometimes contains fluoride dissolved out of minerals. Some regions have a bit of it in their well water naturally. Typically, low levels around 1 parts per million are beneficial for preventing tooth decay. More on that later. But higher levels can cause a condition called fluorosis, mottling of teeth, or other health issues. So what about elemental fluorine occurring naturally? For a long time, chemists believed that free fluorine never occurs in nature due to its high reactivity. However, in 2012, a surprising discovery was made. Tiny pockets of fluorine gas were found trapped in a mineral called antozonite, which is a variety of fluoride. Antozonite was known to give off a weird smell when crushed, earning the nickname like stinky fluorspar. And researchers finally determined that this odor was actually fluorine gas being released. How is that possible? Now, it turns out that antozonite deposits containing traces of uranium underwent natural radiation, which split fluoride atoms out of the crystal lattice, temporarily freeing some fluorine gas that got trapped in inclusions in the mineral. So in these unique radiation-battered crystals, fluorine was basically trapped in tiny cavities. This is an exception to the rule. Practically speaking, you will not encounter free fluorine in the environment. In the broader universe, fluorine is rarer than many nearby elements. Stars don't produce much fluorine. Nuclear reactions in stars actually tend to destroy fluorine. It's thought that fluorine is formed in certain unusual stellar processes, like the outer shells of red giant stars or by cosmic ray interactions. But once formed, fluorine can easily react with hydrogen or other light elements to form fluoride. So it doesn't last long in a star's hot interior. This cosmic rarity means fluorine is less common in the universe compared to elements like carbon, oxygen, or neon. Now, after Henry Moissan's success in 1886, one might think chemists would start producing fluorine gas left and right. But fluorine's wild nature meant that even knowing how to get it, doing so on a large scale would require caution and ingenuity. Industrial production of fluorine really took off in the 20th century, especially during World War II. The Manhattan Project, a U.S. effort to build the first atomic bomb, desperately needed fluorine gas to make uranium hexafluoride for uranium enrichment. This urgency drove the construction of huge electrochemical plants to produce fluorine in ton quantities. And this was actually the first time fluorine was made outside of small lab setups. Now, the methods that were used here were essentially scaled-up versions of Moissan's original electrolysis. So, how do we produce fluorine gas commercially? Well, the primary method remains electrolysis of a fluoride salt in hydrogen fluoride. Typically, the process uses an electrolyte mixture of potassium bifluoride dissolved in anhydrous hydrogen fluoride. When this mixture is heated slightly, about 70 to 100 degrees, it melts and conducts electricity. Now, a special electrolytic cell is used. The container often serves as a cathode, usually made of steel or monel steel, and a carbon rod or block is used as an anode. When an electric current passes through, the fluoride ions are oxidized at the anode to form fluorine gas, bubbling off, while hydrogen ions from the hydrogen fluoride are reduced at the cathode from the hydrogen gas. In summary, the reaction in the cell is this. Now, it sounds pretty simple, but the engineering is tricky. These gases have to be separated properly to avoid recombining. Imagine spending all that energy to make fluorine gas, only to have it touch hydrogen and explode back into hydrogen fluoride. The cell materials have to withstand fluorine's attack. In practice, the interior of the cell forms a protective fluoride layer that helps resist corrosion, and the conditions are controlled carefully. Modern fluorine plants run this process continuously, drawing off fluorine gas and either using it immediately or compressing it into cylinders. Now, it is worth noting that because of fluorine's reactivity, most industries that use fluorine gas generate it in situ, meaning right on site as needed. Shipping large tanks of fluorine around is dangerous and expensive. Imagine a leak. Fluorine spill is far worse than, say, a chlorine leak. So, many facilities will have their own electrolysis units or have fluorine piped directly from a nearby production unit. Globally, tens of thousands of tons of fluorine gas are produced each year. It is not as high volume as some industrial gases, but it's significant, considering how specialized its uses are. Now, aside from the Moissan method of electrolysis, is there another way to get fluorine gas? Well, chemists search for chemical methods because not everyone wants to maintain a nasty hydrogen fluoride electrocell. For a long time, textbooks stated no chemical reaction alone could yield fluorine. Every reagent strong enough to liberate fluorine from a compound would itself form a compound with fluorine. However, in the 1980s, a chemist named Carl Occurrence found a clever two-step chemical route. He used the fact that certain high oxidation state metal fluorides will give up fluorine under the right conditions. Christie's method involved oxidizing potassium fluoride with potassium permanganate in the presence of a strong acid to form a particular manganese compound, then adding antimony pentafluoride to release fluorine gas. Now, it would be complex and not something you would do at home, but it proved a point. Fluorine gas can be made chemically in a laboratory without electrolysis if you have the right exotic ingredients. Still, for all practical purposes, industry sticks to electrolysis as it is efficient and well understood, even if it requires careful handling. Now, the raw material of fluorine production is generally fluoride ore. Fluoride is mined from the earth and then purified. To get hydrogen fluoride, the feed for electrolysis, the mineral is reacted with concentrated sulfuric acid in a kiln, producing hydrogen fluoride gas and leaving behind calcium sulfate. The hydrogen fluoride gas is captured, purified, and either used as hydrogen fluoride or fed into an electrolysis cell to make fluorine. This conversion of calcium fluorine to hydrogen fluoride is a key step, and it's basically the same process used by earlier chemists like McGrath and Scheele. They just didn't capture it safely back then. So from mine to element, the chain is dig fluoride, treat it with sulfuric acid to get hydrogen fluoride, electrolyze the hydrogen fluoride with the potassium fluoride added to get fluorine gas. Every link in that chain requires robust materials due to corrosion. Modern chemical plants often use specialized plastics, alloys, and ceramics to handle hydrogen fluoride and fluorine. Now, fluorine production saw a big uptick in the mid-20th century after World War II. The nuclear industry continued to use fluorine for processing fuel, and the chemical industry found new markets. Companies like DuPont also pioneered large-scale fluorochemical operations in the 1930s and the 1940s. In example, producing refrigerant gases and polymers. More on that next. By the 1980s and the 1990s, millions of tons of fluoride were being mined each year to satisfy the demand for fluorine-containing products. Now, this level has fluctuated with demand. It dipped when CFC refrigerant were banned, then shifted as new uses arose. China, Mongolia, Russia, Mexico, and South Africa are some of the top sources of fluoride today. Now, why go through all of this trouble to obtain fluorine? Well, as it turns out, fluorine unlocks some extraordinarily useful chemicals and materials. The element has found its way into many industries and products, sometimes in surprising ways. Let's explore how fluorine is used from heavy industry to the very toothpaste on your bathroom sink. Now, one of the breakthrough uses of fluorine was in refrigerant gases. In the early 20th century, refrigerators and air conditioners used refrigerants like ammonia or sulfur dioxide, which were toxic and flammable. Chemists discovered that by adding fluorine to carbon compounds, they could create an excellent refrigerant that were stable and non-flammable. Thus were born the CFCs. The chlorofluorocarbons, such as Freon 12, CFCs became the standard in cooling systems and also found use as propellant in aerosol spray cans and in foam blowing agent. For decades, fluorine-containing Freon kept our food cold and homes comfortable. However, there was a dark side to it. The CFC molecules, when released into the atmosphere, would eventually break down, and the liberated chlorine atoms would destroy ozone in the stratosphere, the famous ozone layer problem. In the 1980s, scientists realized CFCs were creating an ozone hole, and an international treaty, the Montreal Protocol, phased out many CFCs by the 1990s. They were replaced by HCFCs and HFCs, hydrochlorofluorocarbons and hydrofluorocarbons, which still contain fluoride but are less harmful to ozone. Now today, newer refrigerators like HFOs aim to be more environmental friendly, but the key point is fluorine in these compounds made them highly stable and effective as refrigerants, even though some of those were too persistent in the environment. The ability of fluorinated molecules to stay inert was exactly what made them attractive for cooling technology. Now, if you ever fried an egg on a Teflon pan, you've appreciated fluorine's contribution. Teflon, the trade name for PTFE, polytetrafluoride ethylene, are we done with these names yet? Is a polymer made of carbon chains completely surrounded by fluorine atoms. The material was discovered accidentally in 1938 by Dr. Roy Plunkett at DuPont when a cylinder of tetrafluoroethylene gas polymerized into a white powder. Teflon's carbon-fluorine bonds are superior strong and the fluorine atoms shield the polymer chain, so it doesn't react with other substances. That's why it's so non-stick and heat resistant. Food adhesives, even molten metal, have a hard time sticking to it or reacting with Teflon. Now, it's not only used in cookware. PTFE coats wires and cables for insulation, lines industrial equipment, and is used in surgical implants. Related fluoropolymers are used in waterproof breathable fabrics like Gore-Tex, which has a PTFE membrane with tiny pores. Rain can't get in, but water vapor can escape. Fluorine-containing rubbers like Vuitton resist chemicals and high temperatures used in seals and gaskets. Essentially, fluorine and polymers give materials incredible durability. They can withstand harsh chemicals and high heat where other plastics would degrade. Now, we know that Teflon has a lot of downsides, and if you want to know more about DuPont and how Teflon is a nightmare in other ways, I'd recommend the Veritasium episode about it. Fluorine's reactive power is harnessed to make other chemicals. One major use of hydrofluoric acid is in oil refining. A process called alkylation uses hydrofluoric acid as a catalyst to produce high-octane gasoline compounds. Hydrofluoric acid is also used to pickle steel, cleaning oxide layers of steel before further processing, and to etch glass for decorative and industrial purposes, like frosting light bulbs or etching circuit boards. We touched on uranium hexafluoride. This is critical for nuclear power and nuclear weapons. Natural uranium must be enriched in the fissile isotope uranium-235, and this is done by converting uranium into uranium hexafluoride gas. Why uranium hexafluoride? Because it's one of the only uranium compounds that is a gas at a manageable temperature. It sublimes at around 56 degrees Celsius. Fluorine is the only element that can make uranium into gas so nicely. Also remember how fluorine has only one isotope. That means that uranium hexafluoride containing uranium-235 is slightly lighter than uranium hexafluoride containing uranium-238. And that difference is what enrichment facilities exploit via centrifuges or diffusion to separate the isotopes. It's fair to say that without fluorine, the nuclear fuel cycle and current nuclear technology would look very different. Another major use is sulfur hexafluoride, a gas used as an insulator in high-voltage electrical equipment like transformers, circuit breakers, and switchgear. Sulfur hexafluoride is extremely good at quenching electrical arcs and has excellent dielectric properties, which means it can prevent sparks and carry high voltages without breaking down. Power grids worldwide relied on sulfur hexafluoride gas for a safe operation and equipment. Now, the downside of sulfur hexafluoride is that it's a very potent greenhouse gas if released, so industries are working on alternatives or recycling, but for now it remains widely used due to its unique properties. One perhaps unexpected area where fluorine shines is in modern medicine. Amazingly, about 20 to 25% of all pharmaceuticals on the market contain at least one fluorine atom in their molecular structure. Why add fluorine to a drug? Because a carbon-fluorine bond can dramatically change a molecule's behavior in the body. Now, fluorine is similar in size to a hydrogen atom, but much more electronegative. So if you swap a hydrogen for fluorine in a drug molecule, that spot becomes more resistant to metabolic breakdown. Enzymes can't digest a CF bond easily. Now, perhaps the most familiar use of fluorine for most people is in fluoride in toothpaste and drinking water. Fluoride, usually as sodium fluoride or sodium monofluorophosphate in toothpaste, or as whatever, we will just write this down, acid, added to water in tiny amounts, has been a cornerstone of dental health for the past half century. The fluoride ions help remineralize tooth enamel and prevent tooth decay. It does this by incorporating into the enamel to form fluorapatite, which is more resistant to acid produced by mouth bacteria. And that brings us to the chemistry question of the week. Ytterbium is a rare earth element named after the village of Ytterby in Sweden. Which high-precision device relies on ytterbium's stable energy levels for record-breaking accuracy? Would that be atomic clocks, Geiger counters, incandescent light bulbs, or lithium-ion batteries? And the answer is atomic clocks. Ytterbium atoms are used in advanced optical lattice clocks that are significantly more precise than standard cesium atomic clocks. Now, not many questions this week, but this one from Chris Morton seemed like a fun one. And the question was, how many stable compounds exist where the formula is also a word, such as clock? Now, using the specific elements chlorine, oxygen, carbon, and potassium, the only stable word compounds are short makers like CO, carbon monoxide, or KO, potassium monoxide. A single molecule spelled clock is chemically impossible because potassium is an alkali metal that prefers ionic bonding, while carbon and oxygen form covalent bonds. Now, these two bonding grammars do not allow elements to snap together in a stable linear chain. Indium arsenic sulfide remains short due to the strict requirements of valence electrons and orbital stability. Now, while you can string together symbols to spell long words like parthenogenesis on paper, these are linguistic coincidences rather than real synthesizable molecules. True chemical stability requires perfectly compatible oxidation states. So I think it is safe to say not that many. I hope I answered your question a little bit. Now, we would like to thank the members that support our channel. Thanks for doing this. We really appreciate you. Now, if you think we missed anything, tell us in the comments. Also, if you want to ask questions. And if you want to know more about another reactive element, take a look at this video about cesium next.